Hi everyone. So this is the second session of writing a Lisp in Python. I'm going to start by setting up the environment like we did last time. So I didn't change anything since last time, as you can see, and we are going to continue the parsing algorithm with the recursive descent parser. I am also enabling the AI auto-completion. And there is something that I have to explain about the Lisp, the representation of Lisp values in the parsing algorithms. So in a Lisp, the read function, which is written this way, is used to parse Lisp values, and all the Lisp values are represented. All the Lisp code is represented as Lisp values. So in order to implement the read function, we need to implement Lisp, the Lisp value runtime. So we are going to start with a very basic type system for Lisp values. We are not going to use the Python runtime for Lisp values because Lisp includes some specific types like cons-cell or lists, linked lists, and because we want the Lisp runtime to be independent from the Python implementation. We are not going to bootstrap everything. Integers, for example, are going to be Python integers, but we are going to add a wrapper over Python values in order to implement our own types. So in dynamically typed language, each value has a type which is known at runtime. So unlike statically typed languages, types are known at runtime. So this is already completed by AI, but the type attribute is what is going to allow us to implement the typing system at runtime. Since we are in a dynamic language, we are going to say that value types are also values, and the data in a value is going to be anything. It can be another Lisp value. It can also be a Python object like an integer or a Python function. Now the first type of values that we are going to add is the value types. So we are going to add a new module for them. This name is not the type's name is not available because it's used by Python libraries, and type is a Python built-in, so we also can't use it. I think that's the part that is probably the hardest part of this project. So I'm going to copy from the previous implementation. Oh, okay. So because we are in the value package, we can use value.types without being hijacked by the Python standard library. So we're going to need the Lisp value types, and we're going to describe types like this, but the type has to be a Lisp value, right? So we can't just use a string, we have to use another Lisp value, but since we have not created a Lisp value, we can't use a Lisp value. So I'm going to use none at first, and I'm going to use a meta type, a type for type values, which is going to be its own type. And it's also going to be its own value. So if I'm in Python, for example, I can use the type function to get the type of a type, and the type of the integer type is type, which is the type function. And the type of type is itself. This is the same mechanisms that I'm using in this language. So the type of the meta type, the type of the type is the type, and the value of the type is the type. And now that we have a type value, we can use it to say that core data types like integer, string, and symbol are instances of the meta type, the type of types. I'm not sure what to put in the value attribute. I think I'm going to do the same thing and say that the value of a type is itself. The value contained in a type is itself, because in Python, for example, if I use int, no, I don't know how to explain it. This is not so this is not a classic value. It's not an integer. It's a type, but I don't know how to represent it. So I'm just going to say that this type exists, and that's it. So the value of the integer type is itself. Then we have the string types. Maybe I could probably use keep the value as none instead of saying that the type is itself. Yeah, that's what I did in the previous implementation, so I'm going to keep it that way. And this is just a list of most types that can be found in any Lisp language, any Lisp implementation. So I'm going to use lists, or yeah, console. If you don't know Lisp, Lisp uses lists that are written this way, but their implementation is not the same as the Python Lisp, the Python lists. In Lisp, the lists are implemented as a pair of values, and each list ends with a special value called nil. So if I wanted to write a Lisp in Python, I would use tuples with 2 elements per tuple, and not an array or a Python list. This has some consequences on the way that lists are used in Lisp. For example, there is a cons function which will concatenate two values. So for example, this is equal to this, and if x is another list, I can create a more complex list by adding elements without modifying the existing x list. So lists in most of the time, Lisp lists are immutable, and they can be combined together to create new lists rather than being mutated with methods like append or pop in Python. So we're going to implement Lisp lists are as a mix of cons cells, which are a pair of 2 elements like this, and a special value that is called nil, which represents an empty list. But I'm going to generalize the nil type. Instead of being specifically for nil, I'm going to use it for most unique values. For example, in Python, there is true, false, none, which all evaluate to themselves, and they are all different from each other. And they don't belong to any type. So for example, true and false are their own type, and none is its own type. So I'm going to keep one single type to be the type of all the unique values, and I'm going to call it unique because it's a unique value. So this types are the kind of value types. These types are Lisp specific, and this one is kind of special. It's a mix of the nil value in Lisp and the non-true false values in most other languages. But it's not specifically used for metaprogramming, so I'm going to keep it here. Then we have symbols. No, we already did it. There are some more data types like arrays and hash tables. I think that's all I'm going to use. This type is not really needed because we already have Lisp cells, but the hash table type is the type that I'm going to be using for environments, for scoping, variable scoping, where each local scope is going to be a hash table. And I'm also going to add function types, but not a single function type. I'm going to add a Lisp function type, which is composed of Lisp expressions with a Lisp parameter list and a Lisp body. There is also the native function types, and in order to describe them, I'm going to be using special values like the evaluation mode, because in Lisp we have usually the function type and the macro type, where macro is kind of a compiler function which executes before running the program. And I'm going to add a third function type, so I'm using the function type as both function and macro and something else, which will be used to implement the axioms used in the Lisp language, like if or define or whatever built-ins are needed. So a function, this function type is going to be the wrapper that can contain either a native function or a Lisp function, but both native functions and Lisp functions will be implemented as Lisp values, which can be manipulated from the Lisp runtime. I had more types in the previous implementation, like char, which is just a character. Ratio is also a type that is often used in Lisp, complex, and this one I'm going to have to implement it as well. I'm going to have to implement this one, but not ratio, complex, and character. I'm also not going to implement them for now, but I plan to do it later. So the box type is kind of like a pointer. It's not a very complex type. It's just something I think can be useful in this language. Same for the struct type. I don't really need it because I already have the hash tables, but it could be useful for transpiling to compiled languages like Rust, which is statically typed and requires specific type descriptions. So I'm going to ignore all of them except the the keyword type, which is Lisp specific, and the Lisp function and native function are going to be different types, but I didn't use this feature in the previous implementation. So it's going. I think it's going to allow the code to be a bit more easier to read by having two types for two different kinds of functions. So now that I have the types, I'm going to comment this one because I don't plan on implementing it now. And I'm also going to move this here because these types are really important for the parser, because I can't parse a Lisp expression without having the symbol type, the const type, or the unique type. But I can very easily skip the hash table type. No, I'm going to have to implement all of them, including the integer, and so I don't think it's useful to make this distinction. So this is function types, metaprogramming types, and data types. So yeah, it's a much better distinction, I think, because data types are types that always evaluate to themselves. So if I run a Lisp interpreter, I don't know if I have one. No, I don't have any. Yeah, I don't have any interpreter right now. So if I use Python, for example, and I write this value, it's going to return the same value. If I write a string, it's going to return the same string. It's not printed the same way, but it's the same string. But if I use a function call, for example, it's not going to return the function call. It's going to try to evaluate it and return the result of the function, if it can. These types are kind of like this. It's not something that is evaluated to itself. A symbol is going to be like any variable is going to evaluate to its value. This is the symbol, and this is what the symbol is evaluated to, which is the contents of the variable. The const type is going to be used for these expressions in Lisp, which are going to be interpreted as this syntax, which is going to be interpreted as a function call, and unique values like none are never going to evaluate to something other than themselves, so I can move them here. And the function types they are not exactly data, so I'm going to keep them separated. So now I'm going to implement I don't know. I think I'm going to start with the unique type, the unique values. So a unique value doesn't really have to have a name. For example, I could say that n is known, but if I try to, if I want them to have a representation that can clearly distinguish them from the other values, I have to give them a name. For example, true has the name, so it has the label true, which means that if any variable is set to true, trying to print it will print true, and not whatever name I gave to true. I also need to compare them. I'm going to make sure that I'm not comparing as unique values anything other than unique values. And if the labels are the same, for example, if the label of A is true and the label of B is true too, then I'm going to return true. So I think I'm going to start writing the reader. So I'm going to start by taking a token, the first token in the list, and then I'm going to check if the token is a value. So for example, it could be a number or a symbol, and if so, then I'm going to return the matching Lisp value. And if that's not the case, if it's for example a syntax element, then I'm going to read an expression with as many tokens as needed until I find the closing parenthesis. And in order to implement this, I will have to import the symbol types, for example, which is not defined yet, so I'm going to have to define it. And there is something with there is something I have to do also. It's with the source mapping. So in the token I have not just a value but also a start line, start position, and other metadata. And these values, I'm not sure if they have to be available when evaluating expressions. So I think that should be as long as it's possible. So for example, if I define a function in Lisp, I need the function object to be able to be aware of where it was defined in the file. But most values won't have this metadata. So in the parsing algorithm, I'm going to define them, and I'm going to add empty values for to be able to inject metadata inside any Lisp value at runtime. So if these values are set to none, this means that these are values that have been created at runtime and not during read time, during the parsing phase. And here I'm going to copy the metadata in the new value before returning it. So this special cases are the most simple one. It's just numbers and symbols. There is also the string that I can do before dealing with recursion. And I'm going to add this exception in order to get a notification when something is wrong, because I forgot to implement something. I'm going to import this, and now I have to define all of them. I am not going to implement unique value parsing. For example, if in my source code I write nil, it's not going to be an axiom of the parser which is going to ignore everything. Nil is going to be a value defined in the built-ins. So there is no special syntax for nil, and I could override what nil is, which is not the case in Python. So for example, if I do this, Python gives me a syntax error because none is a keyword. I'm not going to do that. Nil in my Lisp is not going to be a keyword. It's going to be a simple value. Same for true and false. Yes, there should be enough time. So I'm going to be quickly adding new files for symbols, strings, and integers. And I'm also going to have to implement the cell type, which I named cos here, so I'm going to change it. In Lisp, char and clear are special names, but it's just a convention. It's not a special syntax or something. It's just a convention for the first and the second part of a Lisp const cell. Going to define equality for cells right now. I think I'm going to define it recursively from Lisp, because it can be done with other primitive operations like this and this to access the attribute inside a cell. I'm going to name this cons because in Lisp the function used to create a new cell by combining two values is called cons, because it's a cons cell. Now for integers, it shouldn't be too difficult. I'm not going to define equality because I can just, if I have two values, v1 and v2, I can just do v1 dot value and access the integer inside the value, the Lisp value. So I just need a constructor to simplify creating integers. Same for string. So I'm going to override string with I'm going to recopy this time from integer because it's simpler. It's more close to what I need. And for symbols, because symbols are not supposed to be strings, I'm going to implement them the same way I did for string, but in a different file. I didn't copy the file. So I'm going to define equality for symbols. I didn't do it for strings because they can just access the string value and treat them as Python strings, but symbols are not supposed to exist in Python, so I'm not going to rely on their Python implementation. And unlike strings, which can be sliced, combined, or many other things, symbols just have equality and creation. They don't get processed directly even in Lisp. They get converted to strings first. This should be fine. So now I can try running it. I'm going to create another source file. Instead of calling it source map, I'm going to call it read. So the first step is going to be reading the tokens, tokenizing the first step is going to source map the file, the source map function. I don't know why the AI completion doesn't work. Then I can parse the tokens and I'm going to print the tokens to make sure there is no bug before running read expression, and also to be able to compare the input and output. And then I do this. The read expression is not going to get to read all the tokens. It's only going to read as many tokens as needed to generate a value. So it starts by reading the first token, and then it can create a recursion by reading more tokens until the value is complete. In the previous implementation, I reversed this list in order to optimize for efficiency, because this operation has O of n complexity with n the length of tokens. So for each token that I want to extract, I'm going to have to process the entire token list, and it can be converted to a constant algorithm by reversing the list beforehand. Like this, or more simply like this. And now I don't have to take the first element, I can remove the last element, which has a constant complexity. So this means that my reader is going to work in reverse. Instead of reading the first token and then the second one, is going to read the last one first, and so I have to reverse the array before reading the tokens. I am going to run the parser. Yeah, first bug. So what is value? Oh, okay. So this type annotation doesn't work because the value type is not defined. Okay. Yeah, of course. So I'm starting by reading this when I didn't implement the expression parsing for parentheses. So I'm going to start with strings and symbols. I think I forgot in every I forgot this line in every file. Okay, so we got the first value, which is a number. It should be a number. This is the first token, so that's what should be in the first value, but there is no representation. And there is another problem, which is this kind of problem would be very frequent in this project. In order to it's a circular dependency problem. In order to display this value, I need to have a function that will display the contents of the object, and this function must support many different types of values, but this function must be defined as a Lisp function, and I don't have it, and I can't use Lisp functions for now. So I'm going to define this function in Python as a built-in, a native function built-in. The built-in's name is also reserved in Python for functions that will dynamically access the built-ins as a dictionary, return the built-ins as a dictionary. So I'm going to name it this way, and I'm going to define a print function which takes a Lisp value, or rather a toString function that takes a Lisp value and returns a string that represents the value. What? Why is this indented? Did I forget how to import in Python? Yeah, it's not indenting. Oh, okay, it's because of what was next. So I will need to import all the types. Since the AI completion is not working, for numbers I'm going to cast it as a Python integer, because otherwise it's going to stay as a string, and integers should not be represented by strings. So here I made a very simple string converter that only supports integers. Why is I don't know, AI stopped working. Yeah, better. So now I can, if I, so this about the the exceptions in the special unknown unexpected cases. This is useful because now I can safely process all these tokens, and the toString function is going to raise an error every time an unknown type is converted to a string. So now I have an error for the string. There is one thing that I would like to do, but I don't know how. If I will do a small test. So in Python, types have names, so I'm going to reuse that. So for each type, I'm going to give it a name, which will be used to print which type I am currently printing, because I don't know how to print a type that has no information about itself. So now I can print types, and when I don't know what type I missed, I can do this. So now every time I have something that is not supported, I will have an error that reports exactly what is the type for which toString is not implemented. I think I'm going to stop here. Yeah, the video is quite long already. So now we have the first step of the parser, but it's not complete yet. We have the values for the future runtime environment, and we can parse basic expressions, but we need to implement the recursion part of the recursive descent parser, and this is what we are going to do next time, along with cells and more string conversion cases.